Hi, welcome. This is the first video in the lecture series in Bayesian Statistics. My name is Ruben. I'm one of the professors here at this lecture series. I just started in April at the University of Groningen as a full professor in Econometrics. I'm originally from Sweden, from the University of Gothenburg, and I'm very enthusiastic to start here in this lecture series in Bayesian Statistics. However, before I actually start, I would have to say that even though this lecture series is called Bayesian Statistics, I'm not going to talk too much about Bayesian Statistics. Instead, what I'm going to do is that I'm going to look at, well, the recent developments in statistical data analysis, and these are usually under the name of either machine learning or big data. Well, I'm going to call them machine learning. So therefore you could say that this lecture series is mainly about machine learning. Well, today what I'm going to do is that I'm not going to give you directly a general introduction to machine learning yet, but what I'm going to do instead is that I'm going to give you an introduction for econometricians to machine learning. Well, what is that? Well, I know, of course, that all of you are econometricians already for quite a while. Most of you have done a bachelor in econometrics, and therefore I do think that it would not be very efficient to completely start anew and to say like, well, now at the end of your master, you're almost going to finish a master right now. At the end of your master, we're going to start completely afresh, and now we are going to start with machine learning rather than with econometrics. That I do not think is very efficient, so therefore it is better to start, in fact, the whole lecture series on machine learning, because of the fact that you're econometricians, well, to start with the discussion of a couple of different things. That is, first of all, what is the difference between machine learning on the one hand and econometrics on the other hand? For that, we need to know a little bit more of what we think is econometrics. So that's the discussion that we're going to start with. Then we're going to talk a little bit more about machine learning in general, and we're going to look at the differences between, say, machine learning and econometrics. And then finally, I'm going to finish here with saying some things about, well, how machine learning could actually help you as an econometrician. So that's what we're going to do today. But, well, let me first say a little bit about the introduction towards data analysis. What we can say in general is that nowadays there are two types of data analysis. That is, first of all, statistical or econometric analysis. At the next slide, I'm going to say much more about that. And apart from statistical and econometric analysis, we have machine learning. Well, what you should realize, and that is what I'm going to talk about today, is that even though this is written in a very disjoint way, so that there are two types of data analysis. So either you do machine learning or you do statistical or econometric analysis, but that's of course not true. We will see later on that even though there are big differences between the two, there is also some overlap. Well, as I already said, at the next slide, I'm going to talk about econometric analysis, but before I'm going to do that, let's first of all say a little bit more about machine learning. One of the nice things with respect to at the moment that you have a particular kind of class is that you could in fact, well, think a little bit more in terms of, well, what is actually the definition of machine learning? It would be so nice to say to maybe your friends or your family, well, at the moment I'm doing a course in machine learning, and what is that about? Well, what we can say is, if I have to give such a definition, I would say that machine learning can be roughly described as a set of algorithms that help to understand the data. In this particular definition, we already see a couple of important things. First of all, we see here algorithms. That is quite important because of the fact that machine learning is in that sense quite different from what we are going to see than econometrics. Econometrics is especially about modeling, whereas machine learning is much more about deriving algorithms. And why we're doing that? Well, that's also described here. We do that in order to understand the data. And that is usually by making predictions. So we would like to understand data just because of the fact that we have a particular goal in mind, and that is to make predictions. Well, I'm going to say much more about machine learning later on, but let me now say something about statistical or econometric analysis. But like we have done at the previous slide with respect to machine learning, it is also possible to say something, to give a very brief definition of statistical or econometric analysis. Statistical or econometric analysis is the science that uses stochastic models to describe the data and to use that data to estimate the parameters of that model. Also, in this definition, you can immediately say that there are a couple of things which are important in this definition, especially the stochastic models. These are very important, as I already said. In econometric analysis, models are actually, very central. Again, what they do is to, in this case, to describe the data and take into account, and that is, I hope you have already heard many times before from other professors. At the moment that we're going to do statistical econometric analysis, then we usually make the assumption that the data comes to us in a so-called random way. So that means that at the moment that an econometrician talks about data, then officially he or she is not talking about, say, the data that you have stored on your computer, on your hard disk, on your computer. What you usually are talking about at the moment that you talk about data is some kind of, you could say stochastic model, maybe better to say a stochastic factor. So it has a distribution, and we typically try to, describe this stochastic process, this stochastic factor, by a stochastic model. Well, typically we know a lot about that model, or at least we make assumptions with respect to that model, but there are some things that we do not know. And we usually call them either parameters, as is written over here, or we call them objects. And what we would like to do is that we would like to get information about those objects, to estimate them using, in fact, the data that we have at hand. Well, now you could say that this definition that I have given so far actually is both a definition of statistical analysis as well as econometric analysis. In a sense, you might say that there is not such a big difference between econometrics and statistics. However, at the moment that you're going to look at a course in econometrics, that can be quite different than a course in statistics. And the reason behind that is because of the fact that usually the focus in econometrics is somewhat different from general statistics. And that is to say that at the moment that we're going to look at econometric analysis, then we usually focus on so-called causal relationships. The next couple of minutes, or I think even the next 15 minutes, I'm going to describe causal relationships, but what it usually means is that at the moment that we're going to change some variables in our, say, data, then we would like to know how that is going to change the other variables that we have in the data. That is all about, say, causal relationships. And what we typically do is that we are going to look at causal relationships, which are, as I have described over here, realistic in social sciences. So what you should realize is that data can be quite different in different kind of sciences. So generally we are going to see that in social sciences, we are going to get other kind of data than we typically have in other sciences, such as, for example, medical sciences. And in order to do something with respect to that, we usually try to describe, say, a model that is realistic for social sciences. I write it down social sciences and not economics, because of the fact that you should realize that, fortunate, I would say, or fortunately, the last couple of, say, decades, or at least since 2000, it is not just economics anymore, but for example, also political scientists have realized that using econometrics can be very good for them. Well, now a little bit more about causality. For that, I'm going to use a very standard model that you might already have heard about before. That is the so-called Ruben causal outcome model. Well, it is sometimes called the causal outcome model, but also sometimes called the Ruben causal outcome model. And that's because of the fact that this statistician that we have over here, well, he started to think about this model. He was a statistician, not an econometrician, or he is a statistician, not an econometrician, but because of the fact that it has been used so often by econometricians, for example, James Heckman has been using this causal outcome model quite often. Therefore, we usually use this model as well in econometrics as well at a starting point. In that sense, what we're going to do is that we're going to have variables xi. I is going to run from 1 to n, and they are going to be an IID sequence of observed dummy variables. So important here is that these xi's are going to be observed, so we have them in our, say, data. And we do know what dummy variables are. They are either equal to 0 or 1. And here, more particular, we're going to assume that xi is equal to 1 in the case that I belongs to the so-called treatment group, and xi is equal to 0 if I belongs to the so-called control group. Well, this comes actually from the evaluation literature, and this especially comes from, say, medical sciences, because of the fact that in medical sciences, we usually give somebody a treatment. So, for example, at the moment that you're going to give a vaccine to somebody, well, let's call that a vaccine against a particular kind of disease, say COVID-19. And then what you're going to do is that there are some people that are going to receive the vaccine, so they are going to belong to the treatment group. And there are some individuals that are not going to receive the vaccine, and these are going to be in the control group. Well, in economics, we also usually talk about a treatment and a control group, even in those situations in which there is not really a treatment, or in which at least people don't see that really as a treatment. For example, we could look at the level of education of individuals. And in that particular situation, xi could be equal to 1 in the case that somebody has a university degree, and then xi is equal to 0 in the case that an individual doesn't have a university degree. Well, apart from the treatment variable that we have over here, we typically also have an outcome variable, and that outcome variable we're going to denote it by yi, and also I here runs from 1 till n, and well, you might expect that this yi actually belongs to the xi that we had the previous slide. And yi is going to be, well, determined as follows. Yi is equal to, or either equal to y1 in the case that xi is equal to 1, or yi is equal to y0 in the case that xi is equal to 0. So here we actually have two, well, potential outcome variables. Both of them are random, but they're not necessarily equal to each other. And what we do see is that yi, the observed yi, it's written over here, we observe yi, so yi is what we observe in our data, not these two things that we have over here, but yi is equal to y1 in the case that xi is equal to 1. So that means that we do observe y1 in the case that xi is equal to 1, and in addition to that, we do observe y0 in the case that xi is equal to 0. But this means immediately that we have what we typically call imperfect information. That is to say that we have here that, for example, at the moment that we're going to look at the example of vaccinations, well, then the typical outcome variable is going to be the number of antibodies that an individual has in his or her body. So then y1 is then the, say, number of antibodies that you have in your body at the moment that you receive the vaccine, and y0 is what you will receive at the moment that you're, well, not received the vaccine. So the number of antibodies that you have in the case that you didn't receive the vaccine. Well, this doesn't have to be equal to 0 because of the fact that you might have had COVID-19 itself, so the disease itself. So then in that moment in time, you still have antibodies over here. But there might be a difference between these two things that we have over here. Generally, you expect, of course, that y1 at the moment that the vaccine is going to be effective is going to be larger than y0. But very important here is to realize that you only observe one of the two. If somebody has received the vaccine, then xi is equal to 1, and then you do receive, or you do observe what the number of antibodies are in the case that you did receive the vaccine, but of course you do not observe what that individual would have received or would have had in terms of the antibodies in the case that there was no vaccine, in the case that that particular individual did not receive the vaccine. And the reason behind that is because of the fact that the individual did receive the vaccine. So we cannot say what that particular individual would have had in the case that that particular individual would not have received the vaccine. The other way around is also possible. We have, of course, individuals that did not receive the vaccine. For these individuals, we do observe Y0. So we do observe the number of antibodies that you have at the moment that you did not receive the vaccine, but we do not observe what you would have had in the case that you would have received the vaccine. So therefore, we always observe one of the two. And that's, of course, also true at the moment that we're going to look at educations, at levels of education. Then at the moment that we, for example, are interested in the return to education, then typically the outcome variable in economics is going to be the wage of a particular individual. So then every individual can be thought of having a so-called university wage and a non-university wage, the wage that you're going to receive at the moment that you go to university and the wage that you're going to receive at the moment that you're not going to university. Well, at the moment that an individual went to university, so in the case that xi is equal to 1 in our example, then we do observe the university wage of that individual, but we have no idea about the non-university wage of that particular individual. So to make this example maybe a little bit more clear, let's look at myself. Well, I went to university, so then, well, I do, of course, have then an xi equal to 1. Then I do observe my own wage. At least I know what my wage is. I'm not going to say it over here, but at least I know what my wage is. But even for me, it's going to be hard to say what my wage would have been in the case that I would have decided a long time ago not to go to university. So therefore, we do know Y1, but we do not know Y0. It could also be the other way around. We have, of course, individuals that did not go to universities. To these individuals, we do observe Y0, of course, but you should realize that we do not observe this Y1 that we have over here. So we have to realize that we only observe one of the two. Now we might be interested in the effectiveness of a particular treatment. Then we can look at many different measures with respect to that. But one of the interesting measures that have been looked at so far is the so-called average treatment effect. What is that? Well, first of all, average treatment effect is also always with respect to a particular population. That could be in our case, for example, at the moment that we're going to look at a vaccine, we could, for example, look at the total population that we have here in the Netherlands. We could also think in terms of the, say, education levels of individuals. Well, then it doesn't make that much sense to look at individuals that don't work. So therefore, what we could do is that we could only focus on those individuals that have a very high likelihood to work, say individuals in between 25 and 55 years of age. And then what we can do is that we can look at the so-called average treatment effect. And the average treatment effect is nothing else as the mean outcome of Y1 minus the mean outcome of Y0. So that is, in words, well, the average or mean outcome that we would have observed if everybody in our population belongs to the treatment group minus the mean outcome that we would have observed if everybody in our population would be in the control group. So again, in order to come back to the example that we had before, so let's now look only at the example, the economics example, where we're going to look at the returns to education, then the average treatment effect is a difference from the mean that we would have observed if everybody here in the Netherlands would have gone to university, so even those individuals that did not go to university, minus the mean wage that we would have observed if nobody here in the Netherlands would have gone to university. So even those individuals that now actually went to university. This is an interesting thing to look at, of course. And because of the fact that it's interesting to look at, we would like to analyze it. But what we usually do in econometrics, before asking ourselves the question, could we get some more information about this average treatment effect? The first thing that we usually do is that we look at identification. Identification in econometrics is very central. And the reason behind that is because of the fact that at the moment that we find that a particular object, in this case the average Friedman effect, is not identified, then it makes no sense to try to estimate it. So that's the reason why identification is so important. Now, people usually in econometrics talk a lot about identification, even applied econometricians, but you should take into account that not everybody understands, say, identification that much. However, the idea behind identification is not so difficult to understand. What the idea behind identification is nothing else is that we do already know that the data comes to us in a random way. That means that we can see the data, in this case, the combination of X and Y, as being some kind of random factor. And that random factor, of course, has a distribution function. We do not know it, but it has a distribution function. And now the question arises, the central question in identification arises, if we would have known that distribution function, if we would have known the distribution function of the data, would we then be able to say what our object of interest is? In our case, would we then be able to say what the average treatment effect is? If the answer to that is yes, then our object is identified. If the answer to that is no, even in the case that we do know the data distribution, we don't know what our object is, then our object is unidentified. And then you should realize that even in the case that you would know everything about your population, that is the distribution of your population, then you would not be able to say something about the object of interest, and then it doesn't make any sense to try to estimate. So therefore the question now arises, if we know the, say, data distribution, the distribution of X and Y, would we be able to know what the average Friedman effect is in this case? Well, that is maybe a little bit difficult question to directly answer. So therefore what we typically do is that we first of all are going to ask ourselves the question, well, if we know the data distribution, do we then know this thing that we have over here? And do we then know that thing over here? So are these things separately identified then? If the answer to that is yes, well then of course the average Friedman effect is also identified. Let's first start with respect to the mean of this Y1 that we have over here. What is that thing that we have there? Well, here we can use a very famous trick, and that is the law of iterated expectation. Sometimes also called, well, conditioning on a particular random variable. What I could do here is that I can condition here on the outcomes of X. So this mean of Y1 can be written as the mean of Y1 conditional on X1 equal to 1 multiplied by the probability that X1 is equal to 1 plus the mean of Y1 conditional on X equal to 0 multiplied by the probability that X1 is equal to 0. But that's equal to 1 minus the probability that X1 is equal to 1 in this particular case. Well, this is what I already said, conditioning on another random variable with respect to the mean. I explained that in my preliminaries video. So if you don't know anymore what it is, I'm pretty sure that you have had this before, but if you don't know what it is, well then please look at my preliminaries video. Now if we are going to look here at the right hand side, now the main question becomes, are all these things that we have here at the right hand side, are they identified? Do we know them at the moment that we know the data distribution? Let's first of all look at this thing that we have over here. This is the mean of Y1 conditional on X1 is equal to 1. Well, a very important step that we can actually make over here is that we could say like, well, this can actually be written as the mean of Y conditional on X1 equal to 1. And the reason behind that is because of the fact that we do know that Y1 is equal to Y itself in the case that Xi is equal to 1. So this is actually nothing else. It's the mean of Y conditional on X1 equal to 1. Well, is that identified? Of course is that identified, because of the fact that this only depends on the distribution of Y and X. It depends, of course, on the conditional distribution of Y and X. But you should realize that, well, both of them are a part of our data. So therefore, they belong to the data distribution. So therefore, this part that we have over here is identified. Well, this thing is even much simpler because of the fact that this actually comes directly from X. So an x is a part of the data distribution, it's part of the data at least. Therefore, if we know the data distribution, we know, say, the probability that x1 is equal to 1. That means, of course, that this part over here is also identified. But, well, more difficult is, of course, this part that we have over here. Is this part over here identified? Well, the answer to that is, of course, not. And the reason behind that is because of the fact that, well, at the moment that we are going to look at the mean of y1 conditional on x equal to 0, well, at the moment that x is equal to 0, then we do not observe y1. We only observe then y0. And we only observe y1 in the case that xi is equal to 1. So therefore, we should realize that this part that we have over here is definitely not identified. And the reason behind that is, even in the case that someone is going to give me the data distribution, well, then I don't know anything about the distribution of y1 condition on x equal to 0, because I don't observe that. It's not a part of my data distribution. And therefore, we should realize that this thing that we have over here is therefore also not identified. Well, the same things can be said about this part that we have over here. Also, this part that we have over here is not identified. So therefore, the conclusion that we can make is that the average treatment effect is not identified in our case. Now that we've seen that the average treatment effect is not identified, the conclusion that we can make is that doing any further analysis doesn't make any sense, because of the fact that we cannot get any information from this average treatment effect from the data. That is to say that we cannot, based on the data that we have at hand, we cannot estimate this average treatment effect. That implies that we would expect that, therefore, the econometricians should stop right now and do not any further analysis. Well, that's of course what we don't do usually in econometrics. What we usually do in econometrics is that we are going to recap that what we have done so far is that we have looked at the data generating process. We have defined our data generating process, and therefore we got some kind of assumptions with respect to this data generating process. And so far we have made really light assumptions. And our conclusion is that making these very light assumptions, we cannot identify the average treatment effect. But that doesn't mean, of course, that if we would make additional assumptions, that then we can actually show that the average treatment effect is identified. So therefore, the main question that arises right now is under which restrictions or which assumptions the average treatment effect can become identified. Well, in that sense, it would be good to realize that we do, or we can at least identify some things. From the previous slide, we have already seen that two things are at least identified. That is the mean of y conditional on x1 equal to 1. That's pretty simple because of the fact that that only depends on the distribution of y conditional on x1 equal to 1. And because of the fact that both y and x are observed, they belong to the data distribution, and therefore also the conditional distribution of y conditional on x1 equal to 1, of course, depends on the data distribution. But what we have already seen from the previous slide is that this mean that we have over here is also equal to this mean that we have over here, the mean of y1 conditional on x1 equal to 1. The reason behind that is because of the fact that y and y1 are equal to each other under the restriction that xi is equal to 1. So therefore, this thing is of course identified, but it also identifies the mean of y1 conditional on x1 equal to 1 because of the fact that these things are exactly the same. But the same we can say with respect to this mean that we have over here. Of course, this mean, the mean of y conditional on x1 equal to 0, is also identified, but that is by definition equal to the mean of y0 conditional on x1 equal to 0. So therefore, we could maybe use these two things that we have over here, these two objects that we have over here, in order to say something about the average treatment effect. Well, more in particular, we can ask ourselves the question, under which restrictions the average treatment effect is actually nothing else as the difference between these two things that we have over here. Because you should realize that this thing that we have here at the left-hand side, the mean of y conditional on x1 equal to 1, is almost identical or looks quite like this thing that we have over there, the mean of y1. And of course, this thing that we have over here, which is nothing else as the mean of y0 conditional on x1 equal to 0, looks a lot like that thing that we have over there. So therefore, we could ask ourselves the question is under which restrictions the average treatment effect is exactly equal to the thing that we have here at the right-hand side, because of the fact that if that is going to be true, then the identification of the average treatment effect is going to be completely trivial. Well, because of the fact that we already know that this mean that we have over here, the mean of y conditional on x equal to 1, is nothing else as the mean of y0 conditional, of course, the mean of y1 conditional on x equal to 1. And this thing that we have over here is nothing else as the mean of y0 conditional on x equal to 0. We can also write it like this. And then we get this difference that we have over here. And now it is immediately clear under which restrictions this right-hand side that we have over here is exactly equal to the right-hand side that we had at the previous slide. So this right-hand side that we have over here, and therefore it's equal to the average treatment effect. The answer to that question, is this right-hand side equal to the average treatment effect, is now immediately clear. Well, that is generally only the case if, of course, y0 and y1, they must be uncorrelated with the axis that we have over there, because of the fact that then this mean that we have over here becomes equal to the mean of y1, and this mean that we have over here becomes equal to the mean of y0. So then we have exactly the average treatment effect. In words, that means that what we must have is that the treatment outcome, whether x is equal to 0 or 1, must be uncorrelated with the outcome variables y0 and y1. That is the assumption that you have to make in order to be able to, well, estimate the average treatment effect based on these two things that are identified. But you should realize that that assumption, or in fact, this assumption that we have over here, is not very likely to be the case at the moment that we're going to look at social sciences. And the reason behind that is because of the fact that we should realize that in social sciences, this x, well, that actually varies because of human behavior. Social sciences usually look at human behavior, and therefore this x is most likely some kind of decision variable of a human being. And because of the fact that human beings are smart, at the moment that they make decisions, what they're going to do is that they're going to take into account their potential outcomes of y0 and y1. They at least have some idea about their y0 and their y1. And that means, of course, that it must be the case that the final decision that is going to be made should be correlated with y0 and y1. To come back to the example that we had so far with respect to the decision of your education level, take into account that your education level is usually a decision. Of course, for some individuals, it is more difficult to go to university than for other individuals. But we should realize that still at some stage of your life, you have to make the decision whether you go for higher education or not. Well, at that moment in time, someone is going to take into account, for example, how difficult it is to, in fact, to be able to finish university. In general, therefore, we can expect that individuals that go for university, that try to get a university degree, are in general the more talented, you might say the more, well, the smarter, the more intelligent individuals. And because of the fact that talents are not only important at the moment that you're going to decide about your education level, but they're also going to affect your y0 and your y1, we can expect that the decision whether you go for higher education or not is, well, directly affecting or is affected by this y0 and this y1 that we have over here. So therefore we can expect that in this particular case, y0 and y1, well, are correlated with this X that we have over here. And that is very generally true in social sciences. So the question then arises, what can we do about that? How can we be sure that even though in typical data sets, it's the case that the, say, X may be correlated with Y0 and Y1, how can we be sure in particular situations that they are not? Well, that can only be done at the moment that we're going to do something which is very well known as random control trials, RCTs. What is a random control trial? Well, a random control trial means actually nothing else is that instead of letting individuals in the data set that we have at hand to decide about their axis, we as researchers are going to decide about the axis. And what we're going to do is that we're going to make this X completely random. That is very popular in medical sciences. Well, maybe you could even say that it's the only well accepted way to do research in medical sciences. So if you, for example, would like to prove in medical sciences the, say, effectiveness of a particular vaccine, what do you have to do in that particular situation? Well, then, first of all, what you need is a random sample from the total population. And then what you need to do is that you're going to randomly sample from this random sample, you're going to randomly sample individuals which are going to be receiving the vaccine. So they're going to be in a treatment group, and you have the other individuals, and then also randomly sampled, of course, they're going to be in the control group. And because of the fact that you then know for sure that this X is completely random, and therefore it's not going to be correlated with anything, it should also not be correlated with the Y0 and the Y1 that we have over there. Well, this is very common in medical sciences. As I already said, it's probably the only way in which you can do research in medical sciences. And in a sense, you can also do this, of course, in social sciences, in economics, for example. And I would say there's nothing bad to say about using random control trials in social sciences. If you can do it, then it's pretty fun. But you should take into account that RCTs are not so easy to use in economics and in social sciences in general. And the reason behind that is that there are several practical problems against using them, such as ethical problems, financial, and general equilibrium problems. Well, I'm not going to say too much about that here because of the fact that then I will be able to talk about that for the next couple of hours. But instead, what I'm going to do is that I'm immediately going to jump to the solutions that we as econometricians have brought forward. The first solution is that we are going to make the control and treatment group as comparable as possible. We usually do that by using control variables in regression. What you should realize is that at the moment that you're going to compare the control and treatment group with each other, then of course they're going to differ in terms of the fact that, well, the treatment group of course is going to be treated and the control group is going to be not treated. But they may be different in many, many other respects. For example, if we go back to the example where we had the education level of individuals, well, then we can expect that the individuals who are higher educated are not only higher educated, but they may be different in many other respects, especially with respect to background characteristics. For example, if you're going to compare individuals who are, say, higher educated, and we are going to compare them with their fathers and their mothers, then usually the fathers and the mothers also have higher levels of education, and also the income, the kind of jobs that the fathers and the mothers do are typically different from, say, the average of the total population. For example, if we would ask you here, well, that's now going to be pretty difficult, but what I can do, of course, is ask here around at the University of Groningen, especially among the individuals that do econometrics, what the education level of their father and mothers is. Well, then what I would expect is that it will be higher than the average education level here in the Netherlands. So therefore, we can expect that there is some correlation between, say, the axis that we have over here, but also, in a sense, the background characteristics. And therefore, what we could do is to at least make these, say, background characteristics between the treatment and the control group more comparable to each other, because of the fact that even the observed background characteristics are really quite different from each other, why do we actually expect that therefore the, say, outcomes are going to be uncorrelated with this X that we have over here? That is what we typically do at the moment that we use control variables in regression, but there are of course also other techniques. Now, in many situations, this could help somewhat, but it's not going to help us completely. And therefore, we usually also use another method, and that is to try to use random variation that naturally arises from the data distribution. And this usually goes under the name of natural experiments, but also IV in regression is an example of this second solution that we have over here. And you could actually say that this can be regarded as the most important success of econometrics in, say, the last century. And the reason behind that is because of the fact that even nowadays, many people that are from other sciences than economics or social sciences have the idea that in order to say something about the average treatment effect, what we need is a full randomization. But that's actually not true. Even in the case that we do not have a full randomization, then it's still possible to say something about the average treatment effect that we have over here. Maybe it goes a little bit too far to be able to completely identify it. That depends a bit on the assumptions. But what we should realize is that we can still say something about this average treatment effect, even in the case that we do not have a full randomization of our data. The only thing that we need is that there is some variation with respect to the axis that is completely random. But not all the variation in the axis should be, in fact, random. Well, that means, of course, that we can identify the average treatment effect. And that means that it is possible to estimate or try to estimate at least some parts of the average treatment effect. Well, then estimation in econometrics is usually based on the so-called analogy principle. Well, I discussed the idea behind the analogy principle. I discussed that in my preliminaries video. So if you do not know exactly what the analogy principle is, which is completely based on the law of large numbers, then please look at my my preliminaries video. But what the analogy principle essentially is in words is that if you can write your estimates, the things that you want to estimate, in our case, of course, the average treatment effect, as the expectation of data, then we can use the sample average to estimate it. So that is the whole idea behind the so-called analogy principle. Well, then we have estimators, and we can do the whole estimation process. But before we're going to do that, a very important question, of course, is then still, well, what is the quality of our estimators? Well, in order to say something about the quality of the estimators, a good thing to do is to derive criteria. And in general, well, that is all about statistical inference. But in general, we do have two different criteria. That's first of all consistency. Consistency means nothing else as that at the moment that the number of observations that we have goes to infinity, then it should be the case that the estimator that we have at hand is going to be exactly equal to the thing that we want to estimate, these estimates that we have over here. That's what consistency means. At the moment that we have infinitely many observations, that means nothing else is that we also know the data distribution. So consistency means nothing else is that at the moment that we know the data distribution, well, is our estimator then able to get exactly the correct value of our estimates? Well, that means actually nothing else is that consistency means nothing else is that if we have a consistent estimator, then we do estimate the right thing. So you can also say the other way around. If we have an inconsistent estimator, well, then we don't estimate the correct thing, because even in the case that we are going to have the data distribution, identification already says that we would be able to, well, get the correct value of the estimate, but our estimator is not so great because of the fact that it actually estimates something different. So consistency means that we estimate the wrong, inconsistency means that we estimate the wrong thing. Well, apart from consistency, we also have the criteria of precision. Precision is related to the fact that our estimators are based on data and therefore they're random. So that means that even in the case that we have a consistent estimator, for finite samples, it is going to be the case that our estimators, or maybe better to say, the realizations of our estimators, which are of course estimates, they are not going to be exactly the same as the things that we want to estimate. So therefore, precision says in generally something about how far we off from the thing that we want to estimate at the moment that we have a particular estimator. It says something about the distribution, and the more precise we are, well, the closer we are in general to the thing that we want to estimate. Now you should realize that we usually have a priority with respect to these two criteria. That is to say that we usually, first of all, are going to look at consistency. And then if we have shown that we have a consistent estimator, then we are going to look at precision. And the reason behind that is because of the fact that you should ask yourself the question, what do we have at the moment that we have a very, very precise estimator, which is inconsistent? Well, that means that we are going to have a very, very precise estimator that's going to estimate the wrong thing. Well, you should realize that at the moment that we estimate the wrong thing, precision is not that important at all. Why would we want to estimate something very, very precisely if what we do estimate is actually wrong? So therefore, what we do is that we first of all are going to check consistency. And if we have a consistent estimator, we are going to, well, ask ourselves the question, how precise is that particular estimator? Now, a very interesting detail is that in econometrics, there is generally very little attention to model fit. So usually we don't really look at the question, how well does our final model fit the observed data? So we do, of course, a lot of things. We are going to look at estimators. We are going to look at whether the thing that we want to estimate is identified and whether it's consistent and whether it's very precise. But in the end, we are not that much interested in how well our, say, model does fit the observed data. True, of course, is that at the moment that you're going to look at applied research, at the moment that you're going to look at regression analysis, then it's typically the case that people do report R-squareds. But it's also typically the case that the R-squareds do not get a lot of attention. We just report them and we discuss, well, the value of that particular R-squared, but that's usually done in maybe 1 or 2 lines. And even in the case that the R-squared is going to be low, we're not going to say like, well, this is not a very good model that we have been estimating. So therefore we can run the conclusion, or we can get the conclusion that model fit doesn't seem to be so important in econometrics. Well, that's quite different from what we are going to look at right now, because of the fact that in machine learning, you should realize that everything is about model fit. In machine learning, it is the case that everything is going to be, well, inferior to the idea of model fit. Well, before I actually go on, what I should realize is that so far I have only been talking about machine learning in a general way, and that's what a lot of people do. But you should realize that machine learning actually, well, there are 2 types of machine learning that are quite distinct from each other. First of all, we have unsupervised learning, and the main object of unsupervised learning is to understand the data distribution and to see patterns in that distribution. As I already said a couple of times before, in statistics, and that's also true in machine learning, we're going to assume that the data comes to us in a random way. And that means, of course, that the data has a distribution. And sometimes we would like to see a little bit more. We want to get a little bit more information of that distribution. And that's exactly what unsupervised learning tries to do. Apart from unsupervised learning, you also have supervised learning. The main objective in supervised learning is to predict the outcome variable based on observed characteristics. What I'm going to do over here during this lecture series is that I'm going to completely focus on supervised learning. So even though I will have 1 or 2 slides about unsupervised learning, most of the time I will be talking about supervised learning. And the reason why I actually have chosen for this is actually twofold, but the 2 reasons are quite related to each other. First of all, we do not have that much time. We only have a couple of different lectures. So therefore, I had to make a choice. Of course, I can talk about both of them, but then everything is going to be very superficial. So therefore, I thought it would be better just to focus on 1 of the 2, and that's supervised learning. And the reason, that's the second reason why I actually haven't been chosen for supervised learning. The reason for choosing supervised learning is that at the moment that you look now at machine learning, if you say that you have a course now in machine learning, then lots of people may immediately find that extremely exciting. Lots of people do talk these days about machine learning. Even people who don't know anything about statistics, they still seem to know what machine learning is. And that's because of the fact that you see it actually quite often, for example, in the news, but also a lot of YouTube is actually about machine learning. But you should take into account that as soon as people usually talk about machine learning, and all those nice examples of machine learning are actually never about unsupervised learning. They're always about supervised learning. And the most famous example comes from Facebook. I think that you have already heard about this example before. You have a Facebook account. Suppose that quite a number of you do have a Facebook account. And if you've ever uploaded pictures there, then you might already have seen that at the moment that you upload a picture, then after a couple of minutes, or maybe it's already after a couple of seconds, you see ellipses around the faces that are in that particular picture. And Facebook might even ask you to fill in the names with respect to these different faces. But a question that arises then is, of course, how does Facebook know that there is a face in that particular picture? Well, that's of course not because of the fact that there are many employees at Facebook that draw, say, ellipses all the day around faces. Instead, it is the case that the computers at Facebook do have an algorithm in order to recognize faces. At this stage, I don't have to say anything more about that, but that is actually based on machine learning. It's based on the pixel colors, or maybe better to say on the combination of the pixel colors that you have in the picture. I would like to go on with the differences between, well, econometrics on the one hand and machine learning on the other hand. We have already been talking a lot about econometrics, not that much about machine learning. And an important question that arises right now is, what is actually the difference between the 2? Well, what I could do is that I can talk about that very theoretically, but I do think it's interesting to look at this a bit more in terms of examples. In that sense, the first example that I have over here is about labor economics. I'm an econometrician, but I do have some applications in labor economics. And I do know that being a labor economist, that one of the most important relationships that we have in labor economics is the relationship between education level on the one hand and wages on the other hand. In general, we can expect that higher educated individuals have higher wages. So that means in general that it could, of course, be possible that we have somebody with a very low level of education that has a very high wage. But in general, it is the case that people who are higher educated also receive higher wages. Well, this is, of course, a very important relationship, not only for the individuals, but also it is important for economic welfare, because in economic theory, we do know that there is a relationship between wages on the one hand and productivity on the other hand. In general, we expect that individuals who receive higher wages are also more productive. So therefore, at the moment that the education level in a particular country is higher, that also says something about the overall productivity of that particular country. Well, we as econometricians usually would like to know whether this relationship that we have over here, whether that relationship is also causal, whether there is a causal relationship between education on the one hand and wages on the other hand. That means actually nothing else that we are interested in, whether at the moment that an individual has a higher level of education, that individual becomes more productive and therefore gets higher wages. So that means actually nothing else is that, well, this is the question of whether individuals receive skills at the moment that they go for higher education, and therefore they become more productive and therefore they receive higher wages. But that might not be the only story. It may also be the case that individuals that will go for higher education, these may be more talented, say smarter individuals. It may be the case that people at a particular stage of their life, say 18, have to decide whether they go for higher education or not. If you're very smart, then maybe that decision of going for higher education is very simple. You don't know what to do with your life yet. Of course, you still have your whole life to work. So therefore, why not go to university for a while and do there many, many nice things. And then after that, go for, say, a job. These usually are very talented, very intelligent individuals. If you're not that intelligent, then you may say like, well, maybe better to immediately start working or do something else, but not to go for university because of the fact that that will give me a very bad time. I will not be able to finish it at all. And well, if I would like to finish it, I really have to force myself a lot to study a lot. So therefore we can expect that if this is going to be the case, then it's just the most talented individuals that go to higher education. These are typically, of course, also the individuals who are the most productive. And therefore, in this particular story, it's not that people learn a lot of skills at university, but they are already more productive. And that's the reason why they receive higher wages. Of course, the reality is somewhere in the middle. It is expected that people do learn some skills at universities. Me as a university professor, I would like to at least believe that I learn my, well, the students a bit. That makes them more productive at the labor market. But you should realize that it might also be the case that there is some, what we usually call selection going on here. The most talented individuals go for higher education. And as an econometrician, you would like to know what is really the return to education, in a sense, what makes individuals more, say, skilled, and what results in a sense in these higher wages. You should realize that this question about causality is, of course, what we call policy relevant. The reason behind that, because of the fact that especially universities are usually paid by public money. They're paid out of tax money. And well, to give you a little bit of an idea behind that, if you, in the Netherlands, well, the Netherlands is actually well known for not spending too much money on education. But if you're going to look at the country that I have been in the last couple of years, in Sweden, well, there you do see that, well, in total, about 10 to 15% is spent on education. That is the total based on GDP, not on the public sector, but that's how much is spent on education based on total GDP. And that is, of course, a lot of money, and quite a big chunk of that is spent on university education. If you spend so much money on university education, then you would like to know whether there's really a causal relationship between higher education and higher wages, in a sense that people who go to higher education actually become more skillful and therefore they get higher wages. Or is it just that people are already very talented and therefore receive higher wages at the moment that they went to university? That's really important, because of the fact that if it's just this last, say, spurious relationship that we have, well, then it's better to have the Dutch strategy and spend not too much money on universities. So this is very policy relevant, but now realize that you could be also in another situation. Suppose that you're no longer an econometrician or a policymaker, but instead suppose that you're working in a company and you're working as a manager at a human resource department. And suppose that at a particular moment in time you would like to, or you're considering hiring a new employee, and you of course have the idea what this particular employee has to do, but you still do not exactly know what kind of person you're looking for. That may be possible. And then in that particular situation, what you usually do is that you're going to place a very general ad. And that means, of course, that also the people that are going to react to that particular ad are going to be very, well, wide in terms of characteristics. You will generally have then very high educated individuals, but you may also have very low educated individuals that are going to, well, react to your ad. And the only thing that you need to do as a manager at the human resource department is to choose, well, the best person from the persons that have been reacting to your ad. Well, at that moment in time, you may realize that there is a relationship between, say, whether you received university education and your productivity, in the sense of the higher wages that we have over here. If you know that university, people that went to university are in general more productive, then you also know that, well, among the individuals that have applied to your job, the most suitable individuals may probably be those individuals that went to university. But at the same time, you should realize that in this case, it doesn't really matter that much whether individuals that went to university became more skilled at the university and therefore became more productive, or whether it was the other way around, that these individuals were already very productive, they were very talented, and therefore they went to university, but these individuals were already productive even before the moment that they went to university. That really doesn't matter in this particular case. The only thing that you're interested in is to get, among all the candidates that you have, is to get the most suitable, the most productive person there. And then it really doesn't matter how the real relationship is. So that means that in this case, the only thing that you really would like to do is to predict how suitable, how productive a particular individual is. And well, that is all about machine learning. Of course, this is no longer related to econometrics. In order to give you another example, we could also look at housing economics. Actually, apart from being a labor economist, I have also some papers in housing economics. And here we could start the example by saying that suppose that you have been spiring for a long time a house's website, like, for example, Funda in the Netherlands. I say Funda here because of the fact that I expect most people here in the Netherlands to know Funda, because of the fact that if you're looking for a house, then without making too much advertisement for Funda, then you should realize that it's a good idea to look at Funda because of the fact that most of the houses that are for sale at a particular moment in time, they're listed at Funda. But apart from the fact that you can look for a house there, you can also use that for research. One thing that you could do, as I said, you could try to spider this housing website for a while. Then what you're going to get is house prices, maybe more to say these are not really house prices, not selling prices, but they're going to be asking prices of houses. And you will get a lot of characteristics of these houses, such as the location of the house, the size in square feet, and the number of rooms of these houses. Maybe you're going to get even a little bit more, like say the maintenance of the house or some other characteristics of a particular kind of house. Now suppose, well, this is just for this particular example, but now suppose that house prices are only determined by location and size in square feet. There is a famous saying in the Netherlands that if you ask a real estate agent what are the main determinants of house prices, then this real estate agent will answer that there are actually 3 factors which are really important for house prices. The first of that is, say, the location of the house. The second of that is also the location of the house. And the final important factor is location of the house. That is just to say that location is very, very important for house prices. And that's true, of course, in the Netherlands. We're going to look at, say, house prices in central Amsterdam. They're typically a little bit more expensive than in rural areas here in the Netherlands. But I suppose that this particular real estate agent, well, he or she may only have, well, given an answer with respect to the house prices based already on the size of the house, because of the fact that still it would be a little bit surprising if, of course, a house in central Amsterdam of, say, for example, only 200 square feet, so 20 square meters, would be more expensive than, for example, a house here in Groningen of 2,000 square feet. That would be a little bit surprising. So therefore, we can expect that there are two things which are important for house prices. Well, location on the one hand, and the size in square feet on the other hand. Of course, there may be many, many more things which are important, but let's now assume that these are the only things that were really important in our example. So we're going to make our example not more difficult than necessary. We just assume that only location and size in square feet are important. So anything else, like the maintenance, number of rooms, any other characteristic of a house, is completely unimportant for the house price. But suppose that this relationship is unknown to you. So you would like to know the relationships between house prices and characteristics, but you do not know that, well, the only things that are important are location and size in square feet. In addition to that, to finalize this example, suppose that even though you have here the size in square feet, it is highly measured with error. That means that, for example, suppose that you have a house of 800 square feet. Well, then if you measure it to be equal to 800 square feet, so it's listed here at Vanda for 800 square feet, then it could also be 1000 square feet or only 600 square feet. So that's not that great. But at the same time, we know that the number of rooms, or the rooms, are always of an approximate size of 120 square feet. So that would mean that, for example, if we have a 4-bedroom flat, that must be of, well, roughly the size of 500 square feet. Well, based on all this information, what you could do now is that you could run two different regressions. We, first of all, could run a regression of price on location and the size in square feet. And we could run a regression of price on location and the number of rooms. Of course, you can run many, many more regressions, but suppose that we're only going to consider these two regressions right now. Well, because of the fact that there is a high measurement error with respect to the size in square feet, this regression might not well do so well. The second regression might do much better, at least in terms of fit. We may expect a much better fit with respect to this regression that we have over here. And that's not because of the fact that the number of rooms are so important, but because of the fact that there is this nice relationship between the number of rooms and the size of the house. And probably the number of rooms gives us much more information about the size of the house than actually the size in square feet itself, because of the fact that that's highly measured error. So concluding from this, most likely regression number 2 will give you a better fit. And even in terms of t-values and things like that, probably regression 2 will give you much better t-values than this one that we have over here. So that raises the question, should we then also use regression number 2 in our, say, analysis? Well, you should realize that that depends on the situation. In order to get an idea of where that situation depends upon, let's suppose that you would like to sell your house. So the reason why we have been spidering this website here was not because of the fact that we had nothing to do, but we wanted to do this for our own benefit, and that is selling the house. And at the moment that you would like to sell a house, then typically you would like to have two things. But maybe most important is to get a good price, and you also would like to sell your house as fast as possible. So, and now let's look at two case studies. The first case study is that you're considering contracting a carpenter to build an additional room in your house. That could be interesting, of course, if you expect that houses with more rooms are going to be more valuable, they're going to have a better price. Well, then at that moment in time, it might be interesting to invest a little bit of money in getting an additional room in your house. If you can then sell your house for a higher price, that could be very interesting, of course. You should realize that this case that we have over here is an econometric issue. It is about causality. Is it really the case that at the moment that we're going to increase the number of rooms, then at that moment in time, the price is going to be higher? And based on what we have seen from the previous slide, I haven't really said that, but we can expect that if we run a regression of price on location and the number of rooms, then we can expect that the number of rooms is going to be, well, significantly different from 0, and the coefficient is going to be positive. So that implies that this regression may suggest that it indeed is the case that, well, houses with more rooms have a higher price. So therefore, building an additional room in our house may be good here. But you should realize that from your knowledge of econometrics, you may already say, well, something is going wrong over here. And that is that this is actually a spurious regression. And the reason behind that is because of the fact that the only reason why there is a relationship between the number of rooms and the house price is because of the fact that there is a relationship between the number of rooms and size in square feet. That was in our example. We see here that even though there is no relationship between the house price and the number of rooms, because of the fact that only location and size in square feet is important, we do know that there is a relationship between the size in square feet and the number of rooms that you have. And because of the fact that there is such a high correlation between the number of rooms and the size in square feet, that means that that is the reason why we now see that at the moment that we run a regression of price on location and the number of rooms, that this comes in very positive. But that's not because of the fact that there is a positive relationship. It's in this case just a correlation. And even in the case that I would have included my measured size in square feet in this regression that we've over here, that still doesn't work well because of the fact that this size in square feet is not the real size in square feet. It's highly measured with error. So in this case, what you should do is actually run neither of these regressions that we have over here. What you should do is here, IV. What you should do is first run a regression on size on square feet on the number of rooms that we have over here. And then in a second stage regression, we should run a regression of price on location and on the estimated size in square feet that we have from the previous step, the first step that we have just described. This is all related to econometrics. So our first case that we have over here is only related to econometrics. But now suppose that we are going to look at something else. Suppose that the only thing that you want here is to get a good asking price. So what you want is that you would like to sell your house. You don't want to use a real estate agent in this case who is going to determine the asking price. But instead you're going to do that yourself. So you would like to have a good asking price. And a good asking price is important because at the moment that you set the asking price too high, it might be the case that nobody's going to be interested in your house. You set it too low, well then maybe a lot of people are interested, but they will not give you a good price. So therefore, setting the good asking price is really, really important. Well, in this particular case, at the moment that you would like to set a good asking price, then the only thing that you want to do is based on the data that you have at hand is to make good predictions. And then you should realize that then it doesn't matter that much whether the number of rooms really has a causal impact on the house price, or whether, well, there is some other reason why the number of rooms predicts, well, this house price that we have over here. The only thing that you want in this case is to get a good prediction of the house prices. And then you can do in this case much better by looking at the number of rooms than looking at the size in square feet. So therefore you should realize that this case number 2 is completely related not to econometrics, but with supervised machine learning. We only want to make a good prediction in this particular case. So therefore, what we can conclude from these 2 examples that we have seen so far is that if causal relationships is your goal, then you should use econometrics, so only those things that you have already seen before in all the other lectures that we have seen before in terms of econometrics. If prediction is going to be your goal, well, then it's good to look at my lecture series, because in the fact that then what you should do is to look at supervised machine learning. I would like to go on with the last topic of this first video. And that is about the fact that we have now seen that there are, of course, differences between machine learning on the one hand and econometrics on the other hand. They are not the same. But at the same time, we should realize that they're also not completely disjoint, in the sense that we will see in the next videos that at the moment that we're going to look at machine learning, that a lot of things that you must have learned from econometrics before also hold at the moment that you're going to look at machine learning. On the other hand, it is even the case that even in the case that you decide to do econometrics and not really you're going to perform any machine learning, then even in those cases, it may be the case that it is going to be very valuable for you to use sometimes some tools with respect to machine learning. And I have here 3 different examples with respect to that. First of all, what we could look at is instrumental variable estimation. Going back on that example at the next slide. We can also think of estimation of the treatment group if treatment would not have taken place, such as, for example, in difference and differences. I'm pretty sure that you have heard about this terminology before. Well, at the moment that we're going to look at a treatment group in general, then what we would like to do in the treatment evaluation literature is that we would like to compare the outcome of the treatment group with the outcome that that treatment group would have had in the case that treatment would have not taken place. You're then going to simply take the difference between the 2 outcomes that we have, and you get the effect of the treatment. And take into account that trying to look at the treatment group if treatment would not have taken place is actually nothing else as trying to predict what the outcome of the treatment group would have been if treatment would not have taken place. And we have just seen in the last couple of slides that machine learning is actually very good in making predictions. That is the general topic in machine learning. So therefore, in this particular case, machine learning could be very helpful for you. The last example that I don't discuss here is general predictions of lagging variables in data sets. I would like to come back to this first example. That brings me to incidental variable estimation, and that brings me to a slide that I hope is very familiar for you. It has 2 different equations, or at least this model has 2 different equations. First equation is usually called the outcome equation. It has a yi at the left hand side, and the right hand side we have xi beta 1 plus z1i beta 2 plus ui. And the second equation is usually called the endogenous variable equation. That has at the left hand side an xi, and on the right hand side we have gamma 1 z1i plus gamma 2 z2i plus vi. Very special with respect to this model is, of course, that xi enters the model 2 times. Here is the right hand side variable, and here is the left hand side variable. In addition to that, we allow for the fact that ui and vi, they may be correlated with each other. And you should realize that that is very bad news for the econometrician, because of the fact that that makes it very likely that x and u are also going to be correlated with each other. That can be very easily explained by the fact that what does it actually mean that u and v are correlated with each other? That means in terms, actually nothing else is that even though u and v are random, so we don't know what their outcomes are going to be, at the moment that I know what the outcome of vi is going to be, for example, at the moment I'm going to increase the outcome or the potential outcome of vi, then that says also something about the mean or the general outcome of this ui that we've over here. So therefore, v has an impact on the outcomes of this ui that we've over there. Of course, v also has an impact on xi, because of the fact that, well, the definition of xi is in such a way that vi is at the right hand side of our xi that we've over there. So therefore, we do know that vi, at the moment that I'm going to increase vi, then also xi is going to be increased. And that means, of course, that because of the fact that both ui as well as xi are affected by vi, the outcomes of vi, means of course that it's also very likely to be the case that x and u, they are correlated with each other. And as I already said, that is bad news for the econometrician, because in effect that means that doing a standard ordinary squares regression of yi on xi and zi, well, that, or z1i in this case, that will give us inconsistent estimators of beta 1 and beta 2. But we do know already that there is a way out. At the moment that this z2 that we have over here, we have two restrictions with respect to that z2. First of all, xi and z2 should be correlated with each other. That means in our case, nothing else is this, that this gamma 2 that we have over here, well, that should not be equal to 0. Then, if that is going to be the case, as well as that z2 and ui are not going to be correlated with each other, well, then we can do a little bit more. What this actually means in words is actually nothing else, is that z2, of course, is allowed to have an impact on this yi that we have over here, but it can only be what we can say indirectly. That is to say that, of course, z2 has an impact on xi, that is this assumption that we have made over here. And because of the fact that xi has an impact on yi, we expect z2, as soon as we are going to change the values of z2, that then y is also going to change. But that should not go directly through z2 itself. It should always go through this xi that we have over here, because a direct impact would in fact go through this ui that we have over there. So therefore z2 can only have an impact on yi through the xi that we have over there. But if that is going to be true, so if these two restrictions are going to hold, we do already know that this is usually called instrument relevance, and this is called instrument exogeneity or instrument validity. Well, then in that particular situation, we can do something else, and that is two-stage squares. That means that first of all, we run a regression of xi on z1i and z2i, so that we're going to run simply this regression that we have over here, the second regression that we have over there in the first stage. Then we get estimators of gamma 1 and gamma 2. And then what we can do is that we can predict the mean outcome of xi conditional on z1 and z2. That we can estimate based on the gamma 1 and gamma 2 that we have over here. Lots of people always say that what you actually do in the first stage is that you, in a sense, estimate the outcomes of xi, but that is of course wrong. You should realize that we never do that because of the fact that we already observe the xi, so why would you want to estimate them? But what you do instead is in fact estimating the mean of xi conditional on z1 and z2. And then in a second stage, what we're going to do is that we're going to run a regression of y on the estimated mean of xi conditional on z1 and z2 and this z1 that we have over here. And one of the nice things with respect to two-stage squares is that even though ordinary squares in this case would have given us inconsistent estimators, two-stage squares is consistent. However, there's still a problem with respect to two-stage squares, and that is that two-stage squares is biased. It's a biased method, even though, well, it is consistent. And that for practical situations is of course not so nice because of the fact that usually we do not have many observations. At least we usually don't have infinitely many observations. Consistency is only for the case we have very many observations. And therefore, this bias could actually be large in, say, practical situations. And the question, of course, arises, why do we actually have a bias in two-stage squares? Well, the reason for that is simple. What we could have done, at least theoretically, is run a regression of y on the mean of x condition on z1 and z2, and this z1 that we have over there. If we would have done that, then in that particular situation, we would have had both unbiased and consistent estimators of beta 1 and beta 2. But that's actually not what we do in two-stage squares. We don't run a regression of y on the mean of x conditional on z1 and z2, but what we do is that we estimate the mean in the first stage, because we do not know what the mean of xi conditional on z1 and z2 is. because of the fact that we only know if we know the, say, data distribution. So therefore, in the first stage, what we do is nothing else is try to predict, estimate the mean of X conditional on Z1 and Z2 on the data that we have at hand. And because of the fact that we can make a prediction error in the first stage, we will not generally estimate this gamma 1 and gamma 2 correctly. That goes actually over to the second stage, and that results in a bias in the second stage, in 2 stages squared. But that means, of course, that if we are better able to predict in the first stage, then we will also get a smaller bias and we will get better 2 stages squares estimated. So that means that what we should try to get is the best potential predictions in the first stage. Well, you should realize that, as I already said before, machine learning is very good in that. Without going into details here, what we could have done in this particular case is use the lasso or ridge regressions in the first stage, well, and then substitute them into the second stage and get very good predictions for the mean of X conditional on Z1 and Z2, because the fact that we'll later on see that these methods are very good in prediction. And then we will get, in general, better outcomes than simply run a regression as we typically do in econometrics.